All right, so our next speaker is Celal Ziftci. Some of you might remember him from last year if you were at GTAC last year. Celal presented his culprit finder last year. So he doesn't need introduction, but Celal is now, he now works at Google in the New York office, and his focus has been developer productivity tools for a while. Celal today is going to talk about using data mining and machine learning to improve your monitoring for your applications in production in almost real time.
Yes. Thanks, Sonal. Is it on? Can you hear me? So hi, everybody. As Sonal mentioned, I was a speaker last year at GTAC 2. I was a PhD student back then. I finally finished my PhD. And here I am this year working at Google. Thank you. So I am a software engineer working in the display ads engineering productivity team in New York. I just completed my first year at Google. And the title of my talk is Free Tests Are Better Than Free Bananas. Obviously, this is subjective. So for some of you, it might be better to have free bananas. But in Google, we have free bananas already. So I assumed free tests are better. So. But yeah, like in reality, like what I'm going to talk about is how we use data mining and machine learning to automatically generate test cases so that we can monitor production systems. So I'm going to go over quickly how we release software. I'm pretty sure most of you know about this, and a couple presentations already went over this, but I'll quickly iterate. So we have developers, monkeys again. So they develop software, basically, and then we send the change list that we have for review. Obviously, we test our software, and finally, we release it to production. So the left side is development, the right side is production. So as our systems are running, obviously, we monitor them in real time, continuously. And typically, what we monitor them for is crashes, how much is the memory usage, CPU, QPS, basically the usual suspects that you would expect. And if there's anything out of ordinary compared to the previous release, we will immediately inform a developer, and then they will look at what's going on and maybe go to the previous version, and so on. So obviously, we test before releasing. And the types of testing we do are unit, integration system, all sorts of testing that you can think about. But interestingly, we also test after releases, after we go to production. So you saw some of this in the Netflix talk, I believe. And this is kind of a similar approach, but on a very different level. We already do what you saw in the Netflix talk, like canarying and other things like the monitoring for memory, CPU, crashes. But we also do some very interesting testing after we go to production as well, which I'm going to talk about now. So you might ask, so we already tested before going to production, unit testing, system testing, integration testing. Why are you testing after production? And what are you exactly testing, right? So first of all, our systems are running in production, and they are continuously producing logs. So logs might mean different things for different people. The simplest way to think about them is it's just a text file you keep appending debug logs, information logs, error logs, or you can output some other information about your system, what is your memory usage every 20 minutes, and so on. So these are just examples. And why do we collect this? Obviously, to improve our systems, to see if there's anything out of ordinary. And for my presentation, I'm just going to use this simple log message that we log, which is a dropped banana. It's a banana that's on a tree, and it drops. So I really want to log them. And what I'm logging about this dropped banana is every banana in my system has an ID. Every banana comes from a tree, and that tree has an ID as well. And obviously, bananas have colors, and I also keep information about whether it's ripe or not. Some interesting things here. Obviously, there are some expectations that you might already have, for example, when you look at this log. For example, the ID, it's something that's generated by the system. It's probably non-negative, similar to tree ID. Obviously, a banana that's already dropped should have been in a tree, and so on. So I'll cover these going forward. But yeah, this is basically the simplest thing, the simplest log in our system. So why are we testing? So we have a system, which is the one that I'm focusing on right now on the left side. And this basically interacts with a bunch of other systems that exist inside or outside Google. So let's say our system typically interacts with these two systems, but then those systems in turn interact with some other systems somewhere else. Now, obviously, when we do integration testing or system testing, what we try to do most of the time is we try to bring up all these systems together and actually run tests almost identical to what would happen in production. But this may not be feasible all the time, right? These are big systems, they're distributed, and we may not be able to understand what's actually happening in production. The environment is different in testing versus production. So what then ends up happening is, and by the way, when we are interacting with these systems, we are obviously producing logs. Even in our testing environment, we are logging these logs. And when we test, let's say we are only testing, bringing up the dashed part of this environment and just running this part as a whole. And we are basically leaving out the boxes outside the dashed box. Now, this basically means we are not actually testing exactly how things would happen in production. And obviously, we don't know what happens in production. Things might be different, and we are missing some systems in our testing. That is exactly why we actually want to test things in production. Now, how do we do this? Again, our systems are producing logs, and we have an unlucky developer, which we ask to implement some more test cases. So I specifically call them assertions here to distinguish between where we test. So I call tests the ones that we implement before we go to production, and assertions the ones that we have after we go to production. So an unlucky developer sits down, manually implements these assertions, and we have an assertion framework that basically takes the assertions. As the logs are coming, you just assert them on the logs. And if anything that is not expected happens, then we inform a developer. Now, the assertion framework is pretty typical from what you would expect from a testing framework. Think about JUnit or PyUnit or any other testing framework that you have, with one big difference, though. So when you test before you go to production, you have a closed system. You bring it up, you run everything through it, you run your test cases, the data is output, and you're done. But in this case, our systems are running 24/7, and they're continuously producing logs. So basically, this is, in a nutshell, a testing framework that is running in production continuously, because logs are being produced continuously. So this is the high-level overview of how we do this. Now, let's go through some machinery, some examples, just to understand how exactly things are working. So again, our drop banana example. There's a banana ID there. And say, so this is a kind of good expectation. The ID is always positive, right? So basically, we take this, and we write a test case. It says, assert the banana ID. Given a drop banana, if the ID is greater than 0, you pass. Otherwise, you fail. And you say the ID should be positive. Now, since this is continuously running, let's just go through a couple iterations. So say we are given this drop banana, and the ID is 10. So nothing is out of the ordinary. It runs through. Everything is fine. Another one comes in. This time, ID is 19. It's fine. Whatever. We just keep going. And finally, we get something with a negative ID. So this might happen because we are already in production. Who knows who is using our tool, and they are doing their own schedule of release. Maybe they made a change that caused this, and basically at the end of the day, we log this message, and this is not good because the ID is negative. So because of this, our framework immediately notifies the developer, and the developer is given some information about what is the log that caused the failure, which test case failed. Obviously, this is not our only test case, right? There are some more. And where did it fail, which line, and basically they debug, just they would do in testing before production. And then, obviously, there are different paths. They can roll back the release, or they can try to figure out what exactly happened. Maybe some upstream system is having some problems, and they immediately figure out what's happening and inform the right people. Now, let's look. So this was just one example of a simple assertion that we might have. So I'm going to talk about a bit more of those. So this was the one that we had, banana ID is greater than 0. We might also want to have something like color is either green or yellow. So obviously, we expect bananas to be green or yellow. And finally, This is a very logical thing to expect. If the banana is ripe, it should be yellow. If it's not, if it's green, then it's not ripe. Another type of expectation we have might be the banana with the banana ID must have been on the tree with the tree ID. Otherwise, there was something in our system about our assumptions. Something is wrong, so we have to check it. Now, these are two different kinds of assertions. This first set is what we call stateless assertions. So the reason we call these stateless is because the only thing to assert these on a given log is the log itself. Because I'm not using any information other than what exists in the log itself. Well, obviously the logic is there, but the log is enough, basically. In the second one, though, we call them contextual assertions because we need some context to be able to do the assertion. So in this case, yes, we are given the banana, and we know the banana ID, but we must have some other system where we can check whether this banana was on that tree or not. So basically, we need some external piece of information to run this assertion on the test. Now, given all of these two types of assertions, implementing them is very time-consuming. So most of you are developers, people in software. You know that we spend a lot of time in writing test cases before we go to production. We write unit tests, we do system testing, integration testing. We already spend so much time on it. And as you know, like research says that maintenance is the biggest cost of software systems. So basically, you have to keep maintaining those test cases as well. You cannot just change your code. And this is exactly, again, back to the same problem. These are simply test cases that you sit down and implement manually. And as your system changes, you will have to update them as well. So therefore, it's very time-consuming, and developers are not very happy about these. Now, given this information, how developers are not happy, we went back and looked at this problem again. And specifically, I want to show you something about the first type of assertions that we talked about. So these are the stateless assertions that I talked about. If you think about these are basically invariants, right? So what is an invariant? An invariant is a logical assertion that holds at some point in your system. So invariants come up in a lot of different fields in software engineering. Contract-based programming, for example. You have contracts in your system software, and at the beginning of a function, you make sure that that contract is bound. Like whatever comes into your function adheres to that contract. Another example is you can have defensive programming. So typically, people check these little invariants at the beginning of a function call so that they don't get data that they don't expect. So invariants are basically everywhere already in software engineering. And once we realize these are invariants, we asked us the question, can we actually just mine the logs themselves and to find these invariants? And once we find those invariants, can we actually just automatically generate the stateless assertions? So why do we want to do this? Because we, like our developers, we don't want them to sit down and write test cases again and again. And the answer is yes. So I'm just going to briefly talk about how this works. So our system is generating logs continuously. And we take those logs, and we perform some data mining and machine learning on them, and then come out invariants. So invariants are basically those logical pieces of information, like banana ID is greater than 0. And after we have that information, we generate assertions, which are simply a form of test cases, and generating them is basically a matter of getting some template and just running the invariants through that template, and then generating the actual executable test case itself. And this basically summarizes exactly what we do. And today I'm going to talk about two different data mining and machine learning techniques that we use. And something that's very interesting here is that these logs that we use are the exact same logs that are actually being produced right now, right? We just use them to generate the assertions, and then we run the assertions on the new coming logs in the future. So basically, we just use the existing data to do this. OK, the first one I want to talk about is Daikon. So Daikon is a system implemented by Professor Michael Ernst and his group. He's a professor in University of Washington. Two of his students are actually here. And this system is basically open source. You can just go use it yourself today. And the one thing about Daikon is it basically instruments your system, and then it finds invariants on your source code. So it is specifically mostly targeted for for source code. So what you do is you just run your program with a bunch of test cases potentially, and then Daikon finds invariants on your source code. It says things like, in this function, this was always greater than 0, or in this class, this field is always between 5 and 10, and such. So it basically finds those for you automatically. But it's not exactly geared for data mining and machine learning on data. So it's basically finding things for your source code. But what we wanted to do is to use this on data. So data being the logs. So what we did is we implemented an API on top of it. So that we can programmatically keep, instead of running software, we just keep pushing data to it, and then it finds invariants for us in the data. So basically, we get a bunch of logs. We push the logs through the API, through Daikon. And I will basically give you a high-level overview of how Daikon works logically. So at the beginning, basically, before you push anything, Daikon basically just has a bunch of hypotheses in its mind about what your data is, what your source code or your data will look like. And then you push some of these logs through Daikon, and some of those hypotheses don't hold anymore. For example, let's say you have some field, and Daikon thinks that it's always greater than 10. And it sees some data, and that doesn't hold anymore, so it just eliminates them. It's as simple as that. And then you keep pushing more data to it. It eliminates some more of those in the hypothesis space. And finally, you just keep pushing more logs, and at the end, you are left with these 4 invariants that it finds. The important thing here is this is kind of instead of a constructive way of doing things, this is a top-down way of doing things. So it has a huge space of hypotheses of invariants at the beginning. And as you push more logs, it will actually start eliminating them, and it will have less and less invariants over time. And the more logs you have, the better, because it will observe more data, so its guesses will be more correct. I'm mentioning this because this is basically dynamic analysis, what we call dynamic analysis on your software. And in dynamic analysis, there's a problem in the exploration space. If you don't have enough data, it will find things that actually don't make sense. So if you have more logs, then it's better. And we have a lot of logs, so that's good. All right, so let's look at some examples on what these 4 might be. So Daikon might actually find that banana ID is greater than 0 because it looks at millions of records, and it actually observes that it's always positive. Another thing it might observe is that color is either green or yellow all the time. There are other things that it might observe. For example, banana ID is less than 71. So this clearly is the case in the logs that we push to Daikon. But it's actually not something that we're interested in. It's not useful to us because, as I mentioned, this is dynamic analysis. If we actually kept pushing more and more data, in the ideal case, we would just push, we would have logs that represent the space that we have, log space that we have, but that's basically not possible. So basically, we look at these and say, OK, so banana ID is less than 71. We don't care about it, so we're just going to eliminate it. Similarly, it may be the case that in the logs that we pushed, banana ID is always 3 times the 3 ID plus 4. It happens. I can tell you, we found some equations like this that are just insane. And we were just amazed that it can find those things, but they're just not useful to us. So what we do is basically, we do 2 things. First, we write a simple filter. We filter these things automatically. The first thing we do is we filter things like ID. We don't filter the lower bounds because non-negative is a good thing, but we might actually filter out upper bounds. Or we wrote some filters that just ignore things like timestamps, the usual things that you wouldn't care about. So we automatically filter them out. And then the rest, we basically run to a developer and say, what do you think about these? Do they make sense? And then at that point, it's basically a shopping cart for him. He can just say, yes, this makes sense. Yes, no, this doesn't make sense. He just picks whatever he wants and then tells us these are the ones that are actually logical. So yeah. In a nutshell, this is what Daikon does, and this is how we're using it in Google. And this is already implemented, available. And with that, I'm going to go to the second tool that we use. Now, the second tool that we use is association rule learning. This is basically an algorithm that is very common in data mining. And it was basically invented to analyze database transactions. there's a very famous example where they find that when males shop, they find that whenever they buy diapers, they also buy beer. So they, they rearrange their shopping malls so that those two things are close to each other and so on. So, but yeah, that's just a simple example of how this thing works. So I'm going to still run through an example to show you how this works. So again, we have logs. We push them through this association rule learning algorithm. And it basically takes this as tabular data. It's like a database, basically. And immediately when you look at this, if you look at rows 1 to 4, you realize that whenever isRipe is true, color is yellow, right? So basically, association rule learning can actually find this. And it can output that whenever isRipe is true, this implies color is yellow. Obviously, this may find the reverse. Whenever color is yellow, isRipe is true, which is true, I guess. But we just don't care about this rule. What we care about is the other way around. So we simply basically eliminate this. We ignore it. Or it may find something like whenever the banana ID is not null, tree ID is also not null. This might be the case. It is probably true, but we are not interested in this. It's not useful to us. We simply basically eliminate that. Now, there's one important point here. In Daikon case, Daikon is very suitable for continuously streaming data, because all it does is it keeps a bunch of hypotheses in memory, and then it just filters out, eliminates the ones that don't hold anymore. But in this case, association rule learning, most of the algorithms that are known for association rule learning, they actually work in batch. So in our case, basically, we had to look at the literature, and there are some algorithms that are coming up recently that can actually handle streaming data as well. They have some different characteristics, but they can still find, given enough data, these kinds of good rules. So we are basically looking at those. And finally, just to sum up, this is basically how our assertion framework was running in production. We basically take this unhappy developer and we replace him with our tool where we can just mine invariants from logs and just generate assertions for them. An important point here is, obviously, as I mentioned before, we are doing this only for stateless assertions, not for contextual ones, because for the contextual ones, the search space is just huge. So we are not even attempting to do that. And another important thing here is that even though we are doing this for only stateless assertions, there are two benefits to developers. The first one is, for developers, now this is just a shopping exercise. They just look at the ones that we find and pick the ones that they like. Second, earlier, they had to sit down and manually implement all of this stuff, right? But now, we are actually showing them that what we find in the data. So sometimes they don't even know things exist in the data, because some developer implements the system, the invariant is there, it's not documented, and he puts a test case for it as far as he can tell. But then when we show them these things that we can mine, they go like, oh yeah, that actually makes sense. I actually never thought about it. So basically, those are the two benefits that we can provide to our developers. Hence, free tests are better than free bananas. And I'm going to open it to questions.
Thank you, Celal. More monkeys. I'm pretty sure everybody here will be soon replaced by monkeys, whether or not we migrate to machine learning.
Hopefully,
pretty sure we are close to that. So any questions?
Hi. So 2 questions. One, I don't recall, do you have any examples of a product being built using either Daikon or ARL from the beginning to see, does it drive bugs down? Does it enable better code quality throughout? Any data to show you should use it early and often, or do you wait until you kind of go to prod first?
I don't know of a product. So there's a product called Agitator that uses Daikon. They use it for, I think, something else. But there's research that uses, Daikon is one example of finding likely invariants, right? So there's research that actually supports finding these invariants is actually good for you. Because, whenever you find that something is missing, you'll write test cases for it. Basically, it implicitly increases your code coverage in a way, test coverage.
Okay, that just brought up a different question. So we've had a few presentations so far of different tools. Have you tried taking this approach and merging it with other approaches that have already been shown earlier today to see if together how they impact quality, and if you need all or? variants
Do you have
of
any
them?
specific question or like about a product, or because like we actually do other things? Like for example, Netflix explained how they do canarying and other things. We actually do that as well. But this is just another layer of testing, basically, apart from that.
Oh,
because those are basically like a black box approach onto testing in production, right? Monitoring in production. You just look at memory, you just look at CPU. But I mean, if CPU is up, like lots of things might have gone wrong, right? But this is more like a white box approach. You actually write a test case for it, and then whenever something fails, you immediately know which event it failed on, which log, which line of the test case that you implemented it failed on, and so on. So.
And the API you said you wrote on top of Daikon, is that available for all of us to use?
Not open source yet.
Not yet.
So, but I'm sure we will work with Professor Ernst and make it open source.
Okay, and then the last question was, are they customizable so that, does the source code need to be written in a certain way so that Daikon and ARL can interpret them to find the invariants?
Okay, so in the original implementation, Daikon has front ends for different languages, like C++, Java. But the output format that it has is basically language agnostic. It just outputs its output. That's actually what we do as well. We just create the output that it expects, input that it expects, so that we can just run it through Daikon.
I'm curious, what would happen if all of a sudden there are red bananas?
Red bananas. Well, okay, so if you have a test case for it, obviously we would flag it. You're just asking for color, right? For example, in our example.
Well, let's say right now we live in a world with just green and yellow bananas, and all of a sudden red bananas start popping up in real life.
So what would happen is, like, I think I showed an example of an invariant like that says color is either yellow or green. Right. So we would have a corresponding test case in our test framework that asserts that. And then that would immediately get flagged, and somebody would look at it, why it happened. And then basically what would happen is they would try to understand why we got such a banana, and then try to figure out the system upstream on where this thing is coming from. So I think the most important thing about the whole invariant approach is that if you have them everywhere in your system, so this is like gatekeeping, right? If you do the similar thing upstream, you will actually immediately realize something is wrong upstream as well. So as long as you put these invariant checks everywhere in your system, in between these boundaries, like communication boundaries between systems, whenever something fails, all the teams that are going through this whole failure route will be monitoring, and like they will be notified.
So they can manually modify that invariant if it's actually valid.
Yeah, exactly. So I just showed an example on how to automate it, but as I mentioned, like it's not exactly end-to-end automated. So developers actually still look at them, and sometimes they might say, yeah, like you found that it's either green or yellow, but it might also be blue, for example, right? So they might actually go and change the invariant or the test case itself. So yeah.
Hey, so the machine learning algorithms are kind of sensitive to garbage in, garbage out, right?
Yes.
So are there certain standards for the logging, or like frameworks that you automatically log certain objects or certain method calls or something to support this?
So in Google, we use protocol buffers. So that thing that I showed you is protocol buffers, right? So, and protocol buffers is open source, by the way. Like it's from Google, and lots of people actually use it today. That's what we log. So this basically works on any protocol buffer.
So that would be between systems, I guess? Is that
yeah,
where the logs tend to be?
I basically talked about only part of what this tool can do that I built. And this is just the aspect that we use it for generating test cases. Right. But it can do other things. So I can give you one more example. So just as I showed you in the testing section, we basically bring up our systems and run integration and system tests, right? And during those tests, we still generate logs. So one thing that we did is we ran this same algorithm, machine learning algorithms, on test data as well, and also in production. And then we compared both of them. And there are some interesting things that we found. Like, for example, this is one way of doing test coverage, right? So you look at your invariants, and you realize, oh, like, the invariance that we find on this field is different on production and test. So we should write more tests because we don't have coverage for that.
It's beautiful.
We also have that, but yeah, I didn't talk about that part. So.
My question is, do you have stats on how many errors you actually catch that are useful, and how often does this actually find things that you wouldn't have found through all the other quality means that you have?
So I can tell you for one product, for example, right now we have about 25 assertions that we continue to run in production. And so far we caught 2 production problems, and we immediately fixed them. Sometimes systems are updated. One time they had to change the test cases because something changed in the system, so they had to update the test case. But yeah, like we have been running this for about 6 months now, and yeah, we caught production problems twice.
And one more question is, do developers often learn something about the code from the assertions? If they say, the system says this is an assertion, you're like, oh, really?
Yeah.
I wouldn't have thought that. That might be a problem.
Yes. So definitely. Because, I mean, software companies have a lot of developers, and they come and go, right? And somebody writes some part of the code, and you look at the invariants, and then you realize, oh, I didn't actually realize this was the case, and then they actually learn something from it. So definitely, yes.
Great. Thank you very much, Celal.